where we left. I just want to add two clarifying statements, one about GRW theory or collapse models, and one about the many worlds theories. So as the GRW model is concerned, that came up a bit in the discussion, but I think I didn't say it maybe explicitly enough, that the GRW theory and other collapse models makes in principle predictions that distinguish it from standard quantum mechanics, and thus also for Bohemian mechanics or the many worlds theory. Because the collapse models, they say that the superposition principle, so the linearity of the evolution of the quantum states, breaks down. So it breaks down also fundamentally because you have this collapse, but as we said, the collapse rate for one of few particles is so low that it doesn't make any difference. You wouldn't expect to ever see a single particle wave function collapse, but if you have very large systems, right, you can have a observable deviation from the superposition principle, and there are ways in principle to test this theory and distinguish it from the predictions of standard quantum mechanics or Bohemian mechanics, many worlds, and so on. So this is not conclusive yet, but maybe in our lifetime we will have an answer from experiments whether the collapse models are correct or whether they are ruled out by experiment, and we have to consider one of the formulations of quantum mechanics that do not give up linearity and in which the superposition principle holds on all scales. But I'm not going to say all that much about the collapse models because we will have lectures by Angelo Bassi, I think starting tomorrow or on Friday, I'm not sure. And Angelo Bassi will talk about collapse models, and he is one of the leading experts in the world on collapse models, so he can just say it much better than I can. Another clarification on the many worlds theory, because I was asked during the break. So according to the many worlds theory, and the same will be true also, in fact, in all theories that are candidates for a fundamental description of nature, there's only one wave function, namely the wave function of the universe as a whole. If you take the theory seriously on all scales, then in the end, consequently, in the last consequence, you have only one wave function, the universal wave function. And what we call worlds in the many worlds theories are just different decoherent branches of this one universal wave function. Okay, so I was asked, for instance, twice what happens with energy conservation in this theory, if it's not like somehow the energy of the universe multiplies when you have the splitting of the worlds. But this is not really an issue because you always have the universal wave function capital psi that always evolves according to the fundamental wave equation, let's say a Schrödinger equation, and it's not so clear actually if it makes sense to speak of the energy of the universe, but I mean to the degree that it makes sense, and you want to call this the energy of the universe or whatever for the universal wave function, then this expression is conserved for the universal wave function, even if you have splitting, right? So you have the splitting of these wave functions into different decoherent branches that then correspond to different macroscopic histories, or as we say, different worlds. But in the end, fundamentally, everything happens in one single universe, but one single universal wave function. But where we left, so the last lecture, was that there are two big issues with the many worlds theory. One is how to account for quantum statistics, quantum probabilities, and I don't want to say that the many worlds theory fails in that respect. There are various proposals that we can discuss, maybe at least one of them if we have time. So there are proposals how to explain Born's rule in a many worlds universe, in a many worlds setting, but it's obviously a subtle issue because it's not even clear what those probabilities refer to. Usually we would assume that a measurement reveals just one of many possible outcomes, and we want to know what is the probability for one outcome or the other outcome. But this is not so easy in the many worlds theory, where in any case, both outcomes or all possible outcomes happen. So it's not so easy to say what the probabilities are even referring to. Right? Yes. Yes. Well, in principle, yes. So, I mean, in science, we always kind of assume or live under this fantasy that as experimentalists, we can choose freely what we do. Of course, this is a deep issue, whether this is really the case, because we are also subject to physical laws, at least insofar as we can, talk about us as physical beings, as physical entities. So yes, in some sense, sure, the actions of us as experimentalists will have an influence on how much the universal wave function branches. However, you probably have some sort of branching going on all the time, just not only from controlled quantum experiments, but just from random chaotic quantum evolution, so Schrödinger evolution, together with the coherence. You probably have branching of the universal wave function all the time. So it's not just controlled quantum experiments that create new worlds inside this many worlds universe. Another issue that I want to address is the question. So we are talking about many worlds all the time. The different branches of the universal wave function correspond to different worlds. But how do we find any world at all in the universal wave function? Right? This is a somewhat subtle issue. But if you take the theory seriously, and if you acknowledge that on a fundamental level, there's nothing but the universal wave function, which we should better imagine not as a vector in Hilbert space, because then you are completely lost, but maybe rather in position representation, so to speak, as a function on a very, very high dimensional space, extremely high dimensional space that would correspond to the configuration space of the entire universe. Still, there's a question, how do we get from such an abstract object, right, a wave function, a real valued function on an extremely high dimensional space to represent stuff that we actually experience, which is stuff in three-dimensional space or four-dimensional space-time. So usually, I think what most people do is cheating in some sense, right? So what you want to account for basically is the configuration of stuff in physical space, like a table, let's say, right? And you can imagine a table as a configuration of particles. And one configuration of particles is just one point in this extremely high dimensional configuration, in this extremely high dimensional space, which is the configuration space, which would have approximately 10 to the 23 or 24 dimensions. Right? So one configuration of particles, so to speak, that makes up a table in three-dimensional space is determined by the position of n particles, if you will, in three-dimensional space, right? And this is the one point in the dimension is r to the 3n, right? 3 coordinates for every particle. So the configuration of n particles in three-dimensional space is just one point in this high-dimensional configuration space. Okay? This is relatively easy. This is relatively straightforward. But then, in general, not just one configuration of particles will look like the table we see here, but if we shuffle the particles a bit around, right, if we commute them, or if we change the position of the particles just a little bit, then the configuration, then the table will look macroscopically the same to us, because we do not see the position of every single particle, of every single atom. We have just a very coarse-grained perception of this object. So it's not just one point in this configuration space that will correspond to configurations that look like a table, but there will be, let's say, a whole region of configurations here in configuration space that look more or less macroscopically as a table, right? And then the idea is, I guess, that if you have a wave function that is sufficiently peaked around such configurations, right? If you have a branch of the wave function or a part of the wave function that is somehow peaked, well concentrated on a set in configuration space, right? Which correspond to configurations that would make up a table or a blackboard or a chair or a measurement apparatus or a cat and so on, you are entitled to say that, well, there in the theory there is a chair and there is a table and there is a dead cat and then or an alive cat, right? But this move is a bit questionable. It's a bit questionable not only because this is still a somehow unsharp object that may not be precisely localized, but it's questionable because we are in fact cheating when we talk about this very abstract high-dimensional space, about a configuration space to begin with, right? Why are we entitled to pretend that this extremely high-dimensional space on which the universal wave function lives is a configuration space of anything? If we take the theory seriously, and we have fundamentally only the universal wave functions, not wave functions, wave function, then this is the fundamental physical object and with a fundamental physical space in which this object lives. But there are no particles per se in this theory, right? There's no justification a priori to identify the coordinates in this high-dimensional space with particle positions in three-dimensional space, right? What justifies in a many worlds theory to talk in terms of a hypothetical configuration of particles when you do not really have particles in the formulation of the theory? Okay, this is not an issue that everyone sees, but I think it's an important issue that one should be aware of. And there are people who are trying to give a more precise account, which does not use this trick, this cheating, by calling the high-dimensional space in which the universal wave function lives a configuration space and pretends that it refers to configurations of particles. But then you have to tell a more complicated story and do what, well, the philosophers would call it a functional analysis, right? You would have to analyze how the degrees of freedom of this high-dimensional wave function, how do they interact with each other, right? Are they causally and functionally related to each other, and try to identify in that fashion a world within this universal wave function. But this is an extremely complicated and controversial procedure, I would say. So there is an issue if you have only the universal wave function, and if you want to be realist about this universal wave function, how can we at all identify, locate any world, right? Not to speak of our actual world, but any world at all in this abstract mathematical object. And to drive this point home, it's contrasted. So it's important to note that the GRW theory, the standard GRW theory, has the very same issue, right? So the GRW collapse, okay, makes it, and if you have maybe a superposition of a table here and a table there, right, then it makes it that the wave function collapses, that you are left only with one peak of the wave function concentrated on configurations that correspond to one of the two states, like a table being here rather than a table being there. But it's still a branch of a wave function, right, on an abstract high-dimensional space. There's a difference between the wave function of a table on a high-dimensional configuration space and a table in three-dimensional physical space. So what you can do in GRW theory, and you could do it in principle in the many worlds theory, but that would be besides the point, is to introduce an ontology also for the GRW theory. So you want something in addition to the wave function, which actually refers to stuff out here in physical space, in three-dimensional space or four-dimensional space-time. And you can introduce this also in context of the GRW theory. And I'm not sure if Angelo is going to talk about it, because he knows this, of course, but he's usually a pragmatist and he doesn't care so much about that. But there are these proposals that are discussed in the literature. So one thing you can do with the GRW with a collapsed wave function is to define a mass density. Right? And this is once again a subtle but crucial point. This mass density is a mass density on three-dimensional space. Right? You have here a collapsed wave function on a high-dimensional configuration space, but you define from it a mass density that is a density on three-dimensional physical space. So to say that there is a table here means that there's a lot of mass density concentrated here in the shape of a table and very little mass density or no mass density here. So there's no table in three-dimensional physical space. Okay, but again, this is a subtle but important difference. The mass density exists in three-dimensional physical space. The wave function does not. So it makes sense to say that this table, the theory says that this table corresponds to a mass density that exists in three-dimensional physical space. It does not make sense to say that this table consists of a wave function. Yes? Yes, that's a good question. So they are both ontologies in the sense of stuff that exists in physical space, but particles are just particles. They are just discrete particles with discrete point masses, discrete meta points with positions in space. And the mass density is in general a continuous field. So the GRW mass density theory represents matter as a continuous matter field, basically, not as a configuration of discrete point particles. And this is a proposal for an ontology for the GRW theory. So you want to have something which is really out there in the world that the theory talks about. Sorry? Well, because you have something, you want something that is defined in terms of the wave function. And one possibility, the way to define something in terms of the wave function is to write down this mass density induced by the wave function. And this will in general be a continuous field. I mean, hypothetically, if the wave function were just delta peaks, then you would end up with a discrete density, but this is not a realistic. Yes, right. Even for a single particle, if you have that, you would in general have a somewhat spread out mass density. Right. Another proposal that comes from John Bell is the so-called flash ontology for GRW. And here the proposal is that the collapse events themselves are the ontology, because the wave function does not live in physical space, but the random jumps, okay, the collapse law is formulated in terms of random collapse events, random jumps, whose collapse center is something in physical space. So Bell's idea is that to say that the theory is really about that. The role of the wave function is just to predict the frequency, the occurrence of these collapse events. But what constitutes matter are actually those collapse events that exist as flashes of matter, so to speak, in physical space. So here would be a space-time diagram that shows such a flash ontology. So if you had particles, persistent particles, they would have continuous world lines in space-time. These flashes are just flashes of matter that appear discretely scattered over space-time. And here is Bell, who made these proposals in one of his articles, and he said the GRW jumps, which are part of the wave function, not something else, are well localized in ordinary space. Indeed, each is centered on a particular space-time point, x and t. So we can propose these events as the basis of the local beables. So that means the ontology. Beables is like a play on words that John Bell invented as opposed to observables, right? The word observables, that's usually used in quantum mechanics. He said, no, we don't have to speak about observables. We have to speak about beables, about stuff that is actually there in space and time and a theory describes. So his proposal is to consider these jump events as the local beables of the theory. These are the mathematical counterparts in the theory to real events at definite places and times in the real world, as distinct from the many purely mathematical constructions that occur in the working out of physical theories, as distinct from things which may be real but not localized, and as distinct from the observables of other formulations of quantum mechanics for which we have no use here. A piece of matter, then, is a galaxy of such events. So the last sentence is very nice. So it's this picture, right, that a piece, this table, for instance, is just a galaxy of these flashes, of these matter flashes, so to speak, going in and out of existence as this random collapse occurs. But the collapse law will be such that once the wave function is localized and it doesn't interact anymore, the flashes will occur with very high probability in the same branch of the wave function, so to speak, the same peak of the wave function. So that is why this table would look in the GRW flash ontology like a persistent object. But really it's just, at any moment, there's just this galaxy of flashes that appear in space and time and that make out this object. Yes? Yes. Mm-hmm. Why? Why? How do you make this inference? But you make, so let's leave aside the issue that the wave functions are not exactly delta functions, right? Which is an additional issue, but let's assume they were. Yes. So let's assume you have here I don't know, a delta peak on this point in configuration space. This is a point in configuration space. Can you read it? Or is it too small? Yes. Right? So this is a point in configuration space. Then you would say, how would you identify a table there? You would say, okay, there is one particle at position x1, one particle at position x2, one particle at position x3, and so on, up to trillion particles, and the last particle at position xn. And if you imagine the position of these particles in three-dimensional space, they would form a table. This is perfectly fine, just that you smuggled in particles in there. So you talked in terms of positions of particles in three-dimensional space. Right. This is the whole point. So you're not what... Then you're speaking of particles. Which... Why? then you assume that there are particles in the world. Then you should say that your ontology of your theory, what the theory is about, what it describes, is the position of particles in the world. They are there. But then you should make a theory in which the particle concept is taken seriously. So that the particles, if you have a particle ontology, then the fact that the particles have a position, a configuration in physical space, cannot depend on whether you look at them or not. If you want to take the particle concept seriously, then you should, I think, do a Bohemian theory. Because then you have a particle ontology, then you have a well-defined law of motion for these particles. And then this is what, according to the theory, is actually out there in the world. Right? If you use just the particle concept as if you smuggle it in just as an inferential move whenever your wave function is nicely peaked, this is quite ad hoc. If there are particles in the world or not, should not depend on whether you make a measurement or not. No, so I think most advocates of collapse models, they don't care about ontology at all. So they work with what is sometimes called GRW0, wave function only, and they are completely fine with this picture that you also set. If the wave function is nicely peaked about configurations that make up a certain macroscopic objects, then we can just talk about as if the objects are there. But well, this is a different way of doing physics, and I think even if we are now used to it, maybe through our quantum mechanical education, it's good to think about it and question it. So the point of an ontology, we also say sometimes primitive ontology, is to have a theory that makes a commitment about what is actually there in the world, in space and time. And, yes, and then no, in the mass density, it's not smuggled in. Just in the GRW0, it's smuggled in, when you have just the wave function on a high-dimensional space. Ghirardi likes the mass density one. Yeah. So Ghirardi is an advocate of the mass density one. Angelo is agnostic, at least. So I'm not sure. So I think in terms of primitive ontology, we have here currently 3 proposals for quantum ontology on the table. One is Bohemian mechanics point particle, one is the mass density of GRW, and the third is the flash ontology of GRW. And if you care about ontology, then those are your options. And I personally think there's a good case to be made that Bohemian mechanics is just the most natural choice. It's just the most intuitive and most familiar proposal for ontology, where you just have particles moving on well-defined trajectories. But you can also have an ontology for it. Yeah, sure. Yes. Yes. I don't think there's any good reason. I personally don't think there's any good reason. So if we had discovered basically Bohemian mechanics before the standard Copenhagen quantum mechanics, what would be the reason to give up Bohemian mechanics in favor of Copenhagen? I think there's no good reason. Maybe just positivist philosophy. Sorry? Yeah. Bohemian mechanics? No, because usually for statistical predictions, it's the same measurement formulas. But we will get to that, so maybe we can. Sorry? let me present a theory. So that will be the content of this lecture and probably also the next lecture, and then you can tell me how convincing you find. Yes, it's basically a fundamental notion, a primitive notion. It's, so to speak, flashes of matter. So instead of particles, which are always there and move on a continuous trajectory, these flashes just pop out for an instant, for just an instantaneous moment, and then they are gone. So these are flashes of matter, so to speak. Of matter. So matter, what we call matter, what we see as stuff in physical space, is just, as Bell says, a galaxy of such flash events. So matter is made up of these flashes, according to this proposal. Okay, and those are not as intuitive proposals for ontology as particles, but they are sound. You can understand the world in this fashion. But again, try to understand, it's good to understand what is the point of ontology. Right, you can then say, as many physicists do, that they don't care about ontology in this sense. That's fine, but try to understand what the point is of ontology. The point is really to have a theory that talks and makes a commitment about what is out there in the world, and that really gives you an objective picture of the world in terms of what exists out there in space and time. Yes. Right? Here, where does he say? I'm not sure, I don't see now where the word localized. Okay. Yes, this is this term that he coined local beables, which I was just calling ontology. So Bell said that we need to talk in terms of beables, so in terms of stuff that actually exists out there. And we need something that is localized in space. So you could make a philosophical discussion whether maybe the wave function is also a beable, just a non-local beable. You cannot localize the wave function in physical space. But to make contact, you need some stuff in physical space that is more or less localized. Like particles are localized in space, mass density is localized in space. Sorry? Gravitational forces. So gravitational forces are not local beables in this sense. They're not something that matter could be made up of. Or, okay, no, there are proposals actually that particles or matter are just singularities in the gravitational field. That would then be a proposal for a local ontology. Sorry? No, not necessarily, no. So you can extend it to some, so in space-time, but this is still more or less classical space-time as long as you talk about. Sorry? Yes. No, sorry. I just meant that in principle, there would be a proposal for a primitive ontology, for an ontology of general relativity, for instance. That would be a proposal to say that matter is made, so particles are singularities in the gravitational field. That would be a proposal for an ontology of general relativity. What would not be a proposal for an ontology is canonical anti-commutation algebras. This is not a proposal for an ontology because this is not stuff that exists in physical space. Or, I don't know, spin networks in quantum loop gravity, something. Those might be objects that are relevant to the formulation of the theory, but they are not a proposal for ontology, right? This is not something that you can imagine as being out there in space and time. Yes? Yes, but so should we really get into this discussion? Sure, you can always be skeptical. I think science is, we agree when we do science that the object of science is somehow the common world that we seem to experience, and the theory makes a statement, should make a statement about how this world is like. The theory can turn out to be wrong. It doesn't mean that just that it shouldn't make any statement about the world to begin with. So yes, if we got a bit into this discussion, and now I want to pivot back to Bohemian mechanics. So if you understand the point of ontology, okay, then the real essence of the measurement problem, I think, comes down to this question: what is quantum mechanics actually about? Okay, in standard quantum mechanics, it's not so clear. What is this theory about? Is this a theory about wave function? If so, how do the wave functions relate to our physical world and our experience? Is it a theory about measurements? And what exactly are measurements? Don't we need a theory to understand measurements in the first place? Right? These are not good proposals. If you have an ontology, if the theory makes a commitment about what, according to the theory, there exists in the world, and then the theory describes that, then you cannot have a measurement problem. And you cannot have any sort of quantum paradoxes, right? Because there cannot be anything paradoxical about the configuration of stuff in space and time. If the theory gives you a precise description about what there is in the world, the configuration of stuff in space and time, and what the stuff is made of, then you cannot have a measurement problem, and you cannot have any sort of quantum paradoxes. And I think the simplest theory that does that, the most intuitive proposal for an ontology, is realized in Bohemian mechanics. So in quantum mechanics, we always talk about the wave function as a function on configuration space, at least in the so-called position representation. And this is what we had on the blackboard. So the wave function is a function of n particle coordinates, and this describes a possible configuration. These points in configuration space describe possible configuration of particles. Okay, so now you can ask, what is this n here that appears in the theory? That appears always when you do quantum mechanics. Well, this n is just the number of particles, as it says there. Right? So we assume always when we do quantum mechanics that there is some definite particle number in the system. And this q here, these coordinates, describe the possible configuration of particles. And the mantra, the motto of Bohemian mechanics, very simply put, is just when you say particles, mean particles. Okay, take it seriously that quantum mechanics is a theory about particles that exist in space and time. So if you do that, what do particles, how are they characterized? They are characterized the least that you need, and it turns out all that you need is a position in space. A particle is characterized by its position in physical space. And n particles are characterized by n position in physical space, which we also call the configuration of the system. And then in Bohemian mechanics, the complete state of an n particle system is described by a pair, psi and q, where psi is the wave function of the system and q is the actual configuration of particles at that time. Okay, so in addition to the wave function, the system has an actual configuration in space as given by the position of its particles. Yes. Sure. Yes, in some sense, yes, but you need a law of motion for this QT. And in this law of motion, so what does the particle configuration do? The particle configuration evolves in some sense. Particles move in space, this is what they do. And we need a law of motion for the particles. And this law of motion is the Bohemian guiding equation. And this guiding equation is defined in terms of the wave function. Okay, so the wave function defines a velocity field. We also call it the Bohemian guiding field, along which the particle configuration moves. So there's also where this term pilot wave theory comes from. So the wave function guides the guides the motion of the particles. And of course, this wave function evolves according to the Schrödinger equation. And of course, if we had not discovered the Schrödinger equation, then we would have not discovered this law either. I don't think so, no. There are people who tried it, but no, I don't think it works. And as you will see that the wave function does a lot in this theory. Well, we don't have momentum here to begin with, because we have a first order equation. Yeah. Well, as an analogy, you can a bit think of the wave function as analogous, if you want, to the Hamiltonian in classical mechanics, where the Hamiltonian somehow guides the motion of the system in phase space. Here, the wave function basically guides the motion of the particle configuration in physical space. So one important feature of this theory is that it's first order, so it's a velocity law. The law doesn't give you forces in the sense of accelerations. It determines directly the velocity of the particles. And second, it is a highly non-local equation. So the velocity of the kth particle here depends on the position of all the other particles at the same time. Okay? And of course, this is a feature that you also would have in classical mechanics if you write down Newtonian gravity. The difference being that at least the influences in Newtonian gravity, they decay, so the forces decay like 1 over distance squared, and this is not necessarily a feature that is provided by the wave function. So here the influences do not have to decay with distance or anything. So this law of motion is really non-local in the sense that in principle the motion, the velocity of one particle depends on the position of all the other particles that are entangled with it through the wave function. And this is a feature that at the beginning of the theory, when it was first proposed, actually in 1927 by de Broglie, after it was rediscovered in 52, I think, by David Bohm. I guess this is probably one of the features that people disliked about the theory, that is so highly non-local. Now we know that a correct theory of nature has to be non-local. And we will talk about that hopefully tomorrow when we have time, about Bell's theorem, which proves the non-locality of nature. So if this theory would not be non-local in this sense, then it would be wrong. Okay? Yes? Yeah, I left out here. Here? No, this is the wave function of the system together. So if you no, so in general, it's not a product. That's the point. If it were a product, then you would not have non-local influences here. But in general, so this is a special situation that you have just a product state. The psi? This is as given, so fundamentally, we just have, as in the many worlds theory, the universal wave function. We will talk about that. And from the universal wave function, we get down to wave functions of individual systems. But until we discuss that in detail, just think of this psi as the usual psi given by quantum mechanics. So if you prepare a system with a certain quantum state psi, as you usually do in laboratory, this is the psi that defines for this subsystem, insofar as you can describe it as isolated, defines the Bohemian velocity law. So this is the usual quantum wave function in this sense that defines the velocity of the particles. And so let me just make this point. Bohemian mechanics is defined then by two equations. okay? There's no collapse postulate, no postulates about operators, no postulates about observables, and so on and so forth. There are just two precise mathematical equations. One is the Schrödinger equation that defines the time evolution of the wave function, and one is the guiding equation in which the wave function appears and defines the law of motion for the particles, for the particle configuration. Is there still a question? Yeah. Yes, we come to them. It's just one or two slides ahead. Yes, sorry. Yeah, I just wrote it down in too compact form. Yes, sure. If you have an n-particle system, that is the n-particle. That is the n-particle Hamiltonian. Yeah, I should not have written it down here. So in this compact form. So this x is really a a 3n-dimensional derivative, so to speak, and this v is really usually a sum over pair interactions. So now you can ask the question, where does this guiding equation come from? Because at first glance it looks a bit strange maybe. So this EM is the imaginary part, so this looks a bit strange to consider maybe just the imaginary part. And there are actually many derivations of this law, of this guiding equation. Can derive it, try to derive it from first principles, from Galilean variants if you want, or you can derive it from some sort of Hamilton-Jacobi form of Schrödinger's equation, which is what Bohm did. But I think the simplest derivation comes just from the quantum probability flow. So from the Schrödinger equation, you get straightforwardly a continuity equation. So the continuity equation basically is the conservation of probability for the psi-square distribution. So this rho here is just the psi-square density, and this J is just a probability current, so to speak, that comes out of Schrödinger's equation. So here together you have a probability conservation, and this is a continuity equation, as you might know also from fluid dynamics or from electrodynamics or whatever. And what is a continuity equation? Usually the flow that transports the density, in this sense is the psi-square density, is nothing else than the density times the velocity flow. And if you assume that this quantum probability current is nothing else than the probability density times the velocity flow, you can immediately read off the Bohmian guiding equation, the Bohmian velocity flow from this. Just take this J and divide it by psi-square, and you get the Bohmian guiding equation. Okay, as I said, you can also derive it more from first principles, but this is something that should feel very natural to anyone who knows quantum mechanics. So this is not something very far-fetched or very out of thin air, but this is something that, I mean, everybody knows from quantum mechanics. And if you just take this idea of particle motion seriously, it's really easy and natural to guess the Bohmian guiding equation. Well, yes. Well, plus the, yeah, I mean, here you are already assuming the psi-square probability density, basically, which then later you want to derive. Actually, in Bohmian mechanics, you don't want to assume it. So I wouldn't say that this is a straightforward logical derivation of the law, but it's at least a very strong motivation. But the only thing that's really new in Bohmian mechanics compared to quantum mechanics is that you take the notion of particles seriously, and you take seriously the idea that you have particle positions and you want a law of motion for these particles. And this is, of course, something that was very strange to old Copenhagen quantum mechanics, where people insisted that this is impossible to have particles and well-defined particle trajectories. wouldn't write this, yes. So this you wouldn't write because you wouldn't take this seriously, this velocity field. Bohemian mechanics does take this velocity field seriously. But of course now the only question is, do these two equations describe the phenomena? So I sort of try to motivate it in Bohemian mechanics. So Shelley Goldstein, which is one of my teachers and one of the prime advocates of Bohemian mechanics, he likes to say quantum mechanics is the obvious ontology evolving according to the obvious law. I'm not sure if I want to make such a strong statement, but I want to, I hope I could motivate it. It's a natural choice for ontology, and it's a natural choice for a law of motion, how particles could move. And now the only question is, do these two equations describe the phenomena? And now we will spend some time talking about that, if and how these two equations describe the phenomena. And let's come to the experiment that was already mentioned, the experiment of which Richard Feynman said that it contains actually the only mystery of quantum mechanics, and it is completely unintelligible in classical terms, which is the double slit experiment. Okay, you all know the double slit experiment. You know that like particles or maybe photons are sent through a double slit, and then you see an interference pattern here on the screen. And in terms of wave dynamics, it is easy to understand this interference pattern. It's just Huygens principle, right? How you get interference of waves on the double slit. And remember, actually, fundamentally, the quantum wave function is always a function of on configuration space. But for a single particle, configuration space is just three-dimensional, and you can think about it as a usual wave or field on physical space. And if you would solve the Schrödinger equation for a one-particle wave function on this double slit, you would basically get such an interference pattern. But of course, as you all know, maybe, probably on the screen, you do not see a continuous pattern as you would expect from the wave, but you just see little dots appearing on the screen. And it is really this little dots that make up the interference pattern. And this is just another variation effect of the measurement problem. How do you get from this continuous wave to this discrete dots that appear on the screen? Right? In standard quantum mechanics, here too, you would have to tell some story about state reduction. How do you get from this continuous wave, from this extended wave, to this discrete dots? And now in Bohemian mechanics, right, this problem does not really occur because in addition to the wave, you also have the Bohemian trajectories. You also have the quantum trajectories that are here computed for different initial conditions. So each of these trajectories corresponds to the Bohemian trajectory of one particle, right? And here you see the trajectories for different initial conditions. And here you see one interesting feature. Remember that the Bohemian guiding equation is a first-order differential equation. So if you have existence and uniqueness of solutions, right, you need just one initial condition, one initial position to get a unique trajectory. And this means that different trajectories cannot cross in Bohemian mechanics. So if you have a one-particle situation, it means different trajectories in physical space. You have to be careful. If you have many particle system, it means solutions in configuration space cannot cross. But here, if you have just one particle at a time, then the one-particle trajectories for different initial conditions cannot cross. And this means that in this symmetric setup, this means that no trajectory can cross the symmetry line. Because if there was a trajectory crossing from this lower slit to the upper half, you would also have a trajectory from the upper slit to the lower half, and they would cross. So this is not actually possible. So you see here that the trajectories, the Bohemian trajectories, do not cross the symmetry lines. So in Bohemian mechanics then, you have these actual particle trajectories in addition to the wave. So the wave just determines the motion of the particles, and you send through one particle at a time, and the particle goes either through the upper slit or through the lower slit, depending on the initial condition, and it hits the screen somewhere as determined by the wave function, depending on the initial conditions. And these Bohemian trajectories then give you exactly the interference pattern that you observe in experiment, and that would be predicted by quantum mechanics. Of course, we have to make sure that that the intensity here is exactly the psi-square distribution as would be predicted by quantum mechanics, and this is something that we will discuss either later today or tomorrow. But you see that this is if you compare this, I think, to what is usually said, how this experiment is usually mystified, you know, that you have this wave-particle duality, and sometimes the particle behaves like a wave, and sometimes it behaves like a particle, and it goes through both slits and interacts with itself, and all these things that are usually said about this experiment, and still said to students who want to learn this, and compare this to this very simple, I think, and straightforward and rational picture. And I don't know, to me it seems very obvious. I mean, you have this wave function interferes, but the particle just follows one trajectory. So you have particles and the waves guide the particles, and the particles make up this interference pattern. Yes? Yes, we have to talk about that. Yes, we have to talk about that you get exactly this psi-square distribution. Yes. But you see, this is in principle a perfectly simple and rational picture, and you don't have a mysterious wave-particle duality, some entity that behaves sometimes like a wave and sometimes like a particle, and depending on how you look at it, it's just particles, they move according to a law of motion, and this law of motion is determined by the wave function. And here's also something that at least Bohemian get excited about. I think you've seen it yesterday in the lecture of Alexandre Matsky. You've seen these weak measurements of photon trajectories, right? You've seen that. That were done on photon trajectories. So these are, since they are weak measurements, so each one of these trajectories, they are made up of, they are reconstructed from many, many measurements of an ensemble of photons. So this is not really one single photon that you see there. But you can see that if you look at the weak measurement of velocities, that it gives you precisely the Bohemian velocity law, the Bohemian guiding law. And if you do then these reconstructions of the trajectories from the weak measurements of velocities, you get something that reproduces very well the Bohemian predictions. So of course the standard objections for, still is that these Bohemian trajectories are not observable in general. In general, you cannot know more about the configuration of the system than what is given by its psi-square distribution. This is also something that we want to prove, that we will prove. So in general, you cannot observe the precise trajectory of a Bohemian particle in a strong sense, because if you want to observe the precise trajectory, you have to interact with the system. And by interacting with the system, you change its wave function, thus you change the trajectory. So it's not so, in general, you cannot do a strong measurement of the Bohemian trajectories. But if we widen the scope of measurements, so to speak, to include these weak measurements, there's a sense in which it's no longer true that you cannot observe the Bohemian trajectories. So in this weak sense, you can measure them. The form of the law always remains the same, but the psi that enters the guiding equation is changed if you interact with it. Operationally, it means that you basically, you can no longer regard the system as isolated, right? You have to entangle it, to couple it with some sort of environment, some sort of measurement apparatus. Then you will have some interaction term in the Hamiltonian that describes the interaction between the measured system and the measurement apparatus, and that will then change the wave function. So it will either just change the wave function in a regime where they decouple again, or it will simply entangle the system wave function with the environment wave function, so that the motion of the system depends also on the environment. Yes? I don't think there's a big problem there. Yes. What do you mean, how? So this is we would have to look at it in detail, but there's no issue there, really. So we can look at it later, and because it would take some time, but there's not really issue there, and there's also no retrocausation or anything if you're worried about that delayed choice. Yes, we can look at that later. We have to look at it in detail, but shouldn't be an issue. One important point is this. So if we want to take Bohemian mechanics seriously as a fundamental theory, then we have to regard it, just as we said about the many-worlds theory, as a theory about the universe as a whole. So on a fundamental level, there's just one wave function, okay, which is the wave function of the universe. When we say wave function of the universe, in this case, we don't mean quantum gravity or quantum cosmology or anything. Just in this regime that we talk about, non-relativistic quantum mechanics, we just mean a wave function that is the wave function for all the particles in the universe together. Because on the fundamental level, this is really how the theory is defined. But in general, we do not want to describe the whole universe, of course, when we do some local experiment in our laboratory, or when we want to describe a subsystem. So the question is then, how do we get from the fundamental description of the universe to the description of a subsystem? And the first step is relatively easy. So you have here the configuration space, the huge configuration space of the whole universe, and you split it into degrees of freedom that we call here x, that they belong to the subsystem, and degrees of freedom that belong to the rest of the universe, that is to the environment. So this x could describe, for instance, a single particle that we send through the double slit, or it could correspond to the degrees of freedom of an entire laboratory. But this is the subsystem that we want to describe in terms of an effective description. And analogously, also you have the actual configuration in Bohemian mechanics, the actual configuration of the subsystem and the actual configuration of the rest of the universe. Right? According to Bohemian mechanics, they do have an actual position. And now it's relatively straightforward. You can define something which you can only do in Bohemian mechanics, to define something that we call a conditional wave function for the subsystem, which is take the wave function of the universe, okay, and for the small y, plug in the actual configuration of the rest of the universe, the actual configuration of the environment, which according to Bohemian mechanics exists. And then you end up with a wave function, okay, that depends on the degrees of freedom of the subsystem only. this is now only a function of the x, of the degrees of freedom, the configuration of the subsystem. And the law of motion for the subsystem can then be written in terms of this conditional wave function, right? Because the derivatives, they act only on, sorry, I should have maybe taken out this k here. So this is an x, rather the index is here small x. You have here the derivative acts only on the x coordinates, and of course the y is just implicitly still here in this conditional wave function. But still, this is a very natural object to define. Now you want to go to a description of the subsystem, so you plug in the actual configuration of the environment, and you have a conditional wave function for the subsystem. This conditional wave function is the Bohemian analogon to the usual wave function in quantum mechanics. So if the system is isolated, then this conditional wave function will solve an independent Schrödinger equation. Right? This is the case when basically when you can neglect the interaction between the subsystem and the environment, this will solve an independent Schrödinger equation. If the system interacts with a macroscopic environment, this conditional wave function will collapse in some sense. Statistical predictions for the subsystems will also be formulated in terms of this conditional wave function. So it's important not to distinguish this conditional wave function from the universal wave function. The universal wave function is the fundamental one, but the wave function that we use to provide an effective and statistical description for subsystem is this conditional wave function. And in certain special situations, this conditional wave function has a particularly nice form when it becomes an effective wave function, when we can really forget about the rest of the universe. And this is the case when we can write the universal wave function in this form. So you have one part here, which is basically a product state, a wave function for the subsystem, and a wave function for the universe, for the rest of the universe. But this would be extremely special. However, you can split here off an entire different part of the wave function, of the universal wave function, which does not have to be in a product state at all, but it has to have disjoint y support with this psi here. So for some value of y, either this part here is 0 or that part here is 0. And remember, in Bohemian mechanics, the rest of the universe has an actual configuration, a capital Y. This actual configuration is either in the support of this small wave function or in the support of this psi orthogonal wave function. And if it is in the support of this psi wave function here, you can forget about this whole rest of the universe and ignore it in the description of the subsystem. And then you have an effective wave function after normalization. This is the subsystem gets its own little independent wave function, and you can forget about the rest of the universe. Okay, which is what usually we want to do, at least when we want to treat a subsystem as closed. Okay, so but this is important that we do not assume that subsystems are just closed and shielded from the environment and so on. The fundamental, I mean, you've heard many lectures about open quantum systems, which are very, very important, and usually it's questionable whether you can treat the subsystem really as isolated. But this is all nothing, not an assumption that goes into Bohemian mechanics. It is something that comes out of Bohemian mechanics. So in certain special situation, the theory tells you that you can treat a subsystem as isolated and as described by its own independent wave function. And then we have something, this, as I said, this conditional wave function or this effective wave function, it leads to an effective collapse. Okay, this collapse is nothing in addition, not an additional dynamics that we introduce into the theory. It just comes out of the definition of this conditional wave function. Okay, because if we go back to our just schematic ideal measurement, we have, for instance, a spin measurement, and in the end, we end up with a superposition with, let's say, spin up and pointer pointing to the left, or spin down and pointer pointing to the right. Okay? And these two branches of the wave function, these two terms of the wave function, they are decoherent. Why? Because this measurement apparatus, whether it points to the left or it points to the right, this corresponds to macroscopically distinct states, meaning that the corresponding wave functions have disjoint support on configuration space. Right? A pointer pointing to the left, the wave function of a pointer pointing to the left, is concentrated on a different part of configuration space than a wave function of a pointer pointing to the right. This is why the states are macroscopically discernible. But in Bohemian mechanics, we have the pointer particles have an actual configuration, right? There's an actual configuration of the particles making up the pointer and the measurement apparatus. And they are pointing either to the left or to the right. So they are in the support of either the wave function psi1 or the wave function psi2. And, sorry? Well, one should not use macroscopic as some fundamental term in the theory, but here it is not. So the fundamental formulation of Bohemian mechanics does not require a precise split between microscopic and macroscopic. But if you do such a quantum measurement and couple a system to a measurement apparatus, then it is pretty clear that you end up in a decoherent regime, so to speak. That the wave function that corresponds to a pointer pointing to the left has, for all practical purpose, no overlap with the wave function of a system. It depends on your degree of rigor that you assume. So rigorously, it's quite difficult. It's difficult to prove. But in principle, I would say that this is what you mean by a measurement apparatus. What you mean by a measurement apparatus is some sort of macroscopic system that interacts with a microscopic system and then evolves into one of several possible macroscopically distinct states. So macroscopically distinct means that obviously we see that the states are macroscopically different, right? No, it does not. Yes, sure, but decoherence is part of it. So these are decohered just by the Schrödinger evolution. But the point is that in Bohemian mechanics, the decoherence just means that these two branches of the wave functions, they do not overlap. It does not, but they are still both there. But in Bohemian mechanics, you have in addition the actual configuration of the system that is guided either by one branch of the wave function or by the other branch of the wave function. It depends on the initial conditions, yes. But then we will come to that. So here's a nice animation of a spin measurement. If you have here a wave function of a particle, let's say it has x spin, and you measure the spin in z direction. And what happens here in the Stern-Gerlach magnet, in the inhomogeneous magnetic field, is that the wave function splits. The part of the wave function that belongs to the z spin up component moves up in this inhomogeneous magnetic field. This is something that just comes out of the Pauli equation. And the part of the wave function, the component of the wave function, corresponds to the spin down part, moves down. Okay, this is just something that you get of the Schrödinger evolution. But the problem is, of course, that on the level of the wave function, this is completely symmetric between spin up and spin down. So if you have both parts of the wave function reaching the detector, so to speak, the spin up part and the spin down part. So we get again to the measurement problem. This measurement apparatus would then have to be in a superposition of pointing to the left and pointing to the right. But in Bohemian mechanics, you have in addition the actual position of the particle that is guided by the wave function. And dependent on the initial condition, the actual particle position, determining the actual configuration of the particle, will move either to the left, right, picking out as the actual state of the system than the one in which we have measured spin down, and in which the pointer points to the left. And then we can, for all practical purposes, forget about the other part of the wave function, because it is not guiding the system, because it has effectively decohered. So fundamentally, we haven't changed anything. The universal wave function just goes on following the Schrödinger equation. But the effective wave function, or the conditional wave function, that is just a definition that we use to determine, to give an effective description of the wave function. This collapses effectively for all practical purposes, because we can forget about the other part of the wave function, because it is not guiding the actual configuration of the system. So this is for different initial conditions. The particle position would follow the other part of the wave function that corresponds to, that is guided by the spin-up wave function, and we would end up with a situation in which the pointer points to the right, and we can, for all practical purposes, forget about the other part of the wave function, because this is just empty, and it doesn't guide the particle. And it's important to try to visualize this picture on configuration space, which is always a bit difficult, because configuration space is very abstract. But imagine here, along this axis, you have the degrees of freedom of the wave function, of the electron, right? Which, when it passes the Stern-Gerlach magnet, this wave function splits. One part of the wave function moves up, one part of the wave function moves down. And along these axes, we have the degrees of freedom of the measurement apparatus, which is not, of course, not one-dimensional in reality, but it's 10 to the 24 dimensional. But it's here just represented along these axes. But so the wave function for the system, for the electron, just splits when it passes the Stern-Gerlach magnet. And then what the interaction does is the part of the wave function, so it couples to the measurement apparatus, right? The part of the system wave function that corresponds to spin up, or let's say spin down, evolves into couples with an apparatus wave function that evolves into configuration corresponding to the pointer pointing to the left. Okay, and the degrees of freedom of the electrons corresponding to the electron, to the wave packet that moves up, right? This evolves under the Schrödinger evolution to a state of system plus apparatus in which the system wave functions correspond to configurations in which the pointer points right. Is that clear? Okay, so let's say it one more time. So along this axis, you have the degrees of freedom of the electron of the system wave function. Okay, what happens in the Stern-Gerlach magnet? The wave packet of the electron, it splits. Okay, this is just what happens according to the Pauli equation in the Stern-Gerlach magnet. So you have one wave packet moving up and one wave packet moving down in the Stern-Gerlach magnet. And this means that along these degrees of freedom, okay, the wave function this is the wave function of apparatus plus system, it just splits along this axis. Okay, but here the measurement apparatus is still in its ready state. In its ready state, meaning that along this axis, which is, so to speak, the degrees of freedom of the pointer, it's still in the 0 position, right? And now the wave function of the apparatus, so the degrees corresponding to the degrees of freedom of the apparatus, they will move, this part will evolve into a wave function that corresponds to the pointer pointing to the left, and that part will correspond to a wave function, will evolve into a wave function corresponding to a pointer pointing to the right. This is just what happens under the Schrödinger evolution. Okay, so if the wave function comes in, the part of the wave function, you can think about it, the part of the electron wave function with spin down, that was deflected down, the lower detector clicks. Right, this corresponds here to the lower detector clicking. The part of the wave function that goes up in the Stern-Gerlach magnet reaches the upper detector, if you will. And this corresponds to the upper detector clicking. And this corresponds to configurations that are concentrated here on configuration space. So in configuration space, and this is the high-dimensional configuration space of system plus apparatus, okay, these parts of the wave functions are disjoint. So they are decoherent. But there are still both of them. So we still have the measurement problem, right? If you put here instead of measurement apparatus, you put a dead cat and a live cat, you still have both. You still have the parts of the wave function that correspond to the dead cat and the part of the wave function that corresponds to a live cat, even if they do not overlap. They are both there. However, in Bohemian mechanics, and this is the crucial point, these wave functions do not represent the actual state of the system. But the actual state of the system is represented by or includes the actual configuration of the system. And here the actual configuration of system plus apparatus follows just one of these wave packets. So it evolves either into a configuration in which the particle has moved to the along the spin down wave function and the pointer points to the left, or it corresponds to a configuration in which the particle has moved to the right and the pointer is pointing to the right. Okay, so according to Bohemian mechanics, only one of these wave functions guides the actual configuration of the system, and the other parts of the wave function is empty. Okay, it doesn't mean that it disappears from the world, but it now means that if you write down the conditional wave function, okay, since this other part of the wave function is empty, it doesn't affect the motion of the system anymore. And due to decoherence, we can, for all practical purposes, forget about it, because these macroscopic systems will, with very high probability, never overlap again, to interact again. So what we do here is just as a matter of definition, right? We have this conditional wave function in which we plug in the actual configuration of the system. And this green hill here, this green curve here, now corresponds to this conditional wave function. Okay? And as soon as we have here the first part, just the splitting of the wave packets in the Stern-Gerlach magnet, both parts of the wave function are effective. Okay? Because this is still a coherent superposition. But now, as they evolve into a pointer pointing to the left or a pointer pointing to the right, this coherent superposition gets decoherent. So one part of the effective wave function, the part which is not guiding the actual configuration of the system, becomes zero, because we plug in here the actual configuration of the environment, which here includes the actual configuration of the pointer, which is pointing either to the left or to the right. And if the pointer is pointing to the left, then this part here of the wave function that describes a pointer pointing to the right is zero when we plug in the actual configuration, right? And the other way, or the other way around. If the actual configuration of the system corresponds to a pointer pointing to the right, then plugging this in here for y to get the conditional wave function means that this part of the wave function becomes zero. So we have here an effective collapse. So this explains why we have something like a collapse mechanism and why we can, for all practical purposes, forget about the other part of the wave function. It's no longer effective. It doesn't guide the system. And because this wave function will most likely never ever overlap again, right? This part of the wave function plays no role anymore for the evolution of the system. The evolution is effectively guided just by this part of the wave function. So this is why we have an effective collapse of the conditional, respectively, the effective wave function. And this just comes in as a matter of description. We didn't plug in a collapse postulate, an ad hoc collapse postulate over and above the dynamics. This just comes in from an analysis of the theory, how you treat subsystems of the universe, subsystems of a larger system. It just comes out that if you define this conditional wave function and write down the dynamics for the subsystem in terms of this conditional wave function, this conditional wave function actually collapses in this sense when you have a measurement scenario or when you have some sort of incoherence. But yes, yes, yes. Just, I mean, the crucial part is in this case, in this simple example, that the wave function C1 and the wave function C2 have at least approximately compact support, so that they do not overlap on configuration space, right? And then the actual configuration of the Y system, so the actual configuration in this case of the environment, in particular the measurement apparatus, is either in the support of Psi1 or in the support of Psi2. And then just by definition, if you consider this conditional wave function, okay, and you plug in the actual y of t, the actual configuration of the environment, either this part will be 0 or that part will be 0. So we have an effective collapse. I don't decide, nature decides. And this depends on the initial configuration of the system. Bohemian mechanics is a deterministic theory, and we have to explain, this will be the content of the next lecture, how we explain quantum probabilities. But you see here, it always depends on the initial configuration, of the system, the initial position of the particle. So I have to think about it. I'm not sure what kind, if this is a sort of trait of, but yes, in some sense you can say that. But of course, if you have, it's not like an additional ad hoc assumption or so. If you have a law of motion for particles, you have initial positions, you have initial conditions for the Bohemian law of motion, and these initial conditions will then determine the outcomes. But what is true is that it is a theorem that one has to prove and understand that we cannot know the initial conditions of the Bohemian system with arbitrary precision. So the question, when your question is, where do the probabilities come from? Then in some sense, it's exactly that. So in collapse theories, it's really a spontaneous stochastic collapse dynamics. And in Bohemian mechanics, it is a deterministic theory, but in some sense, it's correct to say that the probabilities come from our ignorance about the initial condition of the system. So we cannot know the initial conditions of the system with arbitrary accuracy. In fact, we cannot know them any better than what is given by the psi-square distribution. And so you get these different outcomes, although they are determined deterministically by the initial configuration of the system. You get either one result or the other with the probabilities predicted by quantum mechanics. And in fact, if you have this highly symmetric setups, it really just depends on which side of the symmetry line the Bohemian particle starts. So in fact, if you have, this is a bit idealized, but if you have this perfectly symmetric setups, if the Bohemian particle starts on the left side of the symmetry line in this case, then it will actually always follow the left wave packet. And if it starts here on the right side of the symmetry line, it will always follow the right packet. Okay, so I'm still here for questions, but now we are pretty good in time. So let's stop here, and the next lecture we will talk about probabilities, how to understand Born's rule, and how to understand the role of operators and observables, how they come into play in this description. Thank you very much.